All right, everyone, we're here to replace the lecture that we missed this morning. So here's a whole bunch of example problems, and I'm just going to work through all of these one by one. I've only worked two of them. I've worked this first problem, and I've worked this problem over here. And all of these other problems are just going to be off the cuff, so hopefully I can figure them out and I don't get stuck, because I don't want to have to record this more than once. That would be a bummer. It's already getting pretty late, and I'd like to go home for the day. All right, so example one. First off, if you'll take your pencil and you'll add a note here. The idea of this problem is that we're launching a projectile from one bucket or one box or one location over a wall into another bucket. So we need to both clear this obstacle and land in this bucket over here. So the location of this wall, this top point we need to clear, is d over 2, 2h. The location of our target is D0, so we're going D out and 0 high. And then you notice we're missing the location here, so if you write this down real quickly, it's 0 in the N1 direction and H in the N2 direction. So first things first, we'll write out our constants like I usually do. I just chose some arbitrary values here. D to 30, H is 5, and G is our regular gravitational force of 9.8. Alright, so then our position, I'll write out my position function. So I write this out right here. So this gives me my position in the N1 direction. You'll notice that it's constant. There's no acceleration. My position simply changes at a constant velocity or a constant rate with respect to time. Whereas in my position for the N2 section, I actually do get a variance in my rate of change thanks to my squared term here. So I do actually have an acceleration in that direction. And one thing to note here is that I have this degree symbol. And so we make this degree symbol by saying escape, DEG, escape. If you don't want to do that, you can also type degree. So the necessity for this is that Mathematica calculates its trigonometric functions in radians. So if you want to make this a more realistic result where it's easily understandable, I would suggest putting it in degrees, and you do it like that above with that actual degree symbology. To create a function for the velocity, we simply take the derivative of the position with respect to time, and we get the following result down here. All right, so a quick note. This is going to be a two-part problem. The first part will be determining a velocity knot and initial launch angle such that I actually clear this initial wall. And then once I clear this wall, I'll then figure out how much velocity I need to add so that I can make it all the way out to this location that I'm trying to hit out here. So step one is that on the very top of this wall, so two things will be true. Number one, I'm going to have this so that my brick or whatever I'm throwing, my projectile, is barely clearing the top of this wall. Its final position will be D over 2 in the N1 direction and 2h in the N2 direction. Secondly, my velocity, I'm going to set my y velocity in the N2 direction to be equal to 0. Why? That'll give me the maximum height for a particular projectile. I'll set that curve right at the very top part of that parabola. And then after that, I can simply increase my launch angle and my velocity, and I'll know that I'll clear the wall every single time. All right, so once I get that, I'll solve for my t, my theta, and my v naught, and I get the following results. So t of a second, theta is 33 degrees, and v naught goes to about 17.8 meters per second. Some other code. I want to be able to plot this thing with respect to time, so I need to pull this time out of this relation. So I divvy that up using this code right here, and then I plot my results. So first off, I plot my position, I replace it with the constants that I initially arbitrarily chose, and then I replace repeat with the theta and the initial launch velocity and the launch angle that I solved for above. So that gives me this blue line, the position of my projectile with respect to time. The other projectile, or this other red line here, is a parametric function that I just wrote to represent the wall. It's got a height of 2h located at d over 2, and I plot it by multiplying by this 1 over time ratio. So as it goes from 0 to time, it'll just go from 0 to 2h, thus giving me this line that runs from 0 to here representing the wall. So as you can see, this particle hits here at the very top, and it looks like the top of the parabola to me, and then it'll continue down on the other side. So the question is now, how do I increase the velocity so that I can determine the final position to actually be on target? So first off, what do I know? I know my position function, I've got my initial constants, and then I've got the constants that I solve for so as to clear the wall. So my little trick here to ensure this clears the wall is that I'm going to add 10 degrees to my launch angle. Why? Well, if I'm throwing a brick or something out in the real world and I'm having it go directly over the top of my wall, it's likely that if I plan for a clearance of, say, like, a couple millimeters, that brick will hit the top of the wall and won't actually go over. So I want to give plenty of space for me to actually clear the wall. So I'm just arbitrarily going to increase my launch angle, and then I'm going to steadily increase my V0 until I have enough range to both clear the wall and hit my final target. So once I increase that velocity, I now have a constant 3 and my regular constants. I solve the same equation as above, but with my final location being D0, this D0 here being given in the initial problem statement. We get our result. We've got our time and our initial velocity. Curiously, it turns out that initial velocity is lower, so it must be that with a greater launch angle, I actually throw the ball a little bit farther. So plot this thing, and instead of before, where you notice that my plot landed exactly at the top of the wall, I've increased my launch angle, so I go right over the top of the wall, and I come down to hit my target located at 30 and 0. So everything checks out. My initial launch height was 5, and D is 30. So therefore my wall should be located at 15 and should be about 10 high, so check there. Launching at 5, going to 30, and hitting at the ground. So everything checks out, and since I kept everything in symbolic notation, I can come up here and say change this height to maybe say 20. So I have a much taller wall now, and I'll just reevaluate this whole section of code. So I have to launch, looks like much higher into the air this time. I've got a 70-degree launch angle. And I'll come down here for my final plot, and yeah, now I've got a lower 6 seconds in the air, but I still clear the wall, and I still come down and I hit my 30 mark. I've just got to launch the ball a lot higher into the air to clear the obstacle this time. So a tricky problem for sure, but a little manipulation, and you're able to figure it out. All right, so on to the next problem, example 2. So we'll hit Command 4, and we'll type in example 2. Close this cell up so I don't have to see it anymore. All right, so all of these questions will be to determine the position of the block or the particle as a function of time. So here in this thing, I've got my motor, I've got a pulley, and I've got a mass on the motor. So let's develop a force-motion relationship. So my force-motion relationship is equal to, I've got mg pulling downwards, so I'll make the downwards direction negative, and in fact I've defined positive x as going upwards. So minus mg plus 2t, so I get a tension for each side of this pulley, is equal to mx double dot of t. So now to solve this as a function of time, I'll say desolve my force-motion relationship, comma x of t, comma t. Evaluate and solve. I've got an error here. Looks like I forgot my second equal sign. I'll plug that in, and I've got my result. As a fast notice, whenever I make a mistake of accidentally assigning something like that, I'll usually clear the kernel to make sure that I don't get a false result, like some symbol will stay stored on accident, and that'll accidentally throw my results off. Alright, so in this case that didn't actually happen. I still get the same position function, and I wasn't given any initial conditions, so I just leave it as this. I've now got my position of my particle as a function of time and as a function of whatever tension this motor is putting out. Now instead, let's say that I wanted to solve this thing as a function of position rather than a function of time. Now to do that is quite simple. we'll just take that force motion relationship and we'll come down here, and I'll, instead of saying this x double dot of t, I'll say my velocity as a function of position times dv dx. So the derivative of v with respect to x is v dot with x in our parentheses. So I've got exactly the same thing, except now my independent variable, our independent function, is v with respect to x, with the independent variable being x. Evaluate and solve, and bam, I've got my result as a function of position, in case I'm curious as to the velocity as this thing goes upward. And we'll type in the solution here, and we'll minimize this. I'll save this in case my computer crashes, and we'll move on to example 3. Command 4, example 3 solution. So onto this inclined plane. So the question is, I've got a block sitting on a surface, and it has some initial velocity v0 moving down the surface, and then all of a sudden maybe I've got a rope attached to this block, and I apply the force 3t squared minus t to the block. The question is, how long does it take the block to stop? Alright, so we'll make a force motion relationship to test out this this equation, this geometry. Alright, so first things first. How do I write my components of my gravitational force within the plane of the block? How will I balance it in that direction? So remember, the hypotenuse, or any force we apply to any object, has to be the hypotenuse of a triangle. So what do I mean by that? I mean that any components of that force I apply always have to be less than the actual force. So let me bring up my drawing tools here, and let's do an insert, a new graphic. And now I'm going to make a drawing. So I'll draw out this this inclined plane. So there's one side, and down here, and then another line down at the bottom. All right, so I've got gravity acting downward. I've got gravity acting straight down like this. It's actually, instead of doing this, let me put in an arrow instead. All right, so I've got gravity acting straight down. So what I'm curious is, what is the component of gravity that's acting in this down the plane in this direction? So like I said, the actual gravity force has to be the component that is the hypotenuse of some triangle. So to make this, I'm going to drop a right triangle to the inclined plane like such. So I'll get a component perpendicular to the surface like this, which is smaller than this hypotenuse, and then my gravitational component will be along this surface right here. All right, so I know that this angle right here, where my cursor is equal to theta, which makes, if I have make this a triangle right here, this angle theta right there, or 90 minus theta, 90 minus theta, and then theta right here. So if my gravitational force is mg, and I want to figure out what this component is right here, that's opposite of this angle right here, so this component will be sine theta mg. So therefore, my force motion relationship for this block is that FMR is equal to minus sine theta mg, where negative is going down the ramp, minus sine theta mg, plus the force that I'm applying, 3t squared minus t, so 3t raised to the second minus t, and this is going to be equal to the mass of whatever my block is times x double dot of t. Sorry, I'm losing my voice. I spent the whole weekend out of town and was at a lot of loud places, so I seem to have gotten quite hoarse over that time. Now to solve, we'll do a desolve, a force motion relationship. We'll solve it with respect to x of t, slash dot t is my independent variable, and we'll evaluate. All right, boom, I've solved my differential equation. I've got some initial constants in here. So we are given some initial conditions here, so I'm going to say that my initial velocity v naught, let's see, x dot of 0 is equal to v naught, and we'll just set my initial position to be 0 or whatever it starts on the ramp. We'll just define that position as 0. So x of 0 equals 0, x prime equals x naught, and we'll evaluate. And we've got our result. So x of t then equals this function right here. We'll call this my position function. As usual, say x of t slash dot, and then slash slash first to get this into a straight function. To get the velocity with respect to time, we just simply take the derivative of my position with respect to time. So the derivative of the position is given as that, and now we'll solve this position for when it's equal to 0, because that tells us when my velocity is 0. So solve vel with vel equals 0, comma t, and holy smokes, that's a complex answer. I'm glad we didn't have to solve that by hand. So hideously complex. Let's do a slash n here to see what pops up. Anything? No? All right. Let's imagine that I've got some actual values in here. Maybe I've got some constants that say my mass is equal to 1, my gravity is 9.8, and my theta is maybe 30 degrees. So I can either say 30 degree like that, or I could say 30 escape degree escape, 30 degrees. And if I type this in then and say slash dot constants here, still got a hideously awful result, and it still has this v naught constant in it. So we'll define that v naught as well. Let's say my v naught is say 1. V naught is 1, and evaluate. Did I replace that? Oh, did I call it v0? Yeah, I called it v0. All right, so make that v0 instead. All right. So first thing we notice is that we've got this seems like these imaginary terms here, but let's be honest with ourselves. This value here is times 10 to the minus 16. That seems like a rather small value, and in fact, for those familiar with computer programming, we call that the machine error. So to get rid of that, we'll do a slash slash chop, and that'll chop out that machine error and set it equal to 0. All right, so we've got a couple values here. We say that the time that this thing is equal to 0 is this time here and this time here. So to plot out the correct route, we probably have to plot this a couple times to determine what our real result is, whether or not it's the 3 or it's this 0.19. All right, so that's that example. Let's move on to example 4. So command 4, example 4 solution. Actually, let's go back to example 3 real fast. All right, let's plot this out. So we've got my velocity right here. Let's plot my velocity function over t from t equals 0 to 3 seconds. We need to replace these constants, slash dot constants. All right, so we're looking for the times when our velocity is equal to 0. So as time increases, my looks like I have my velocity immediately starts decreasing, and then I have zero velocity here, and then interestingly enough, so this is our slope here, so this is velocity. So we come down to zero velocity here. We have negative position all throughout here. Then we come back to positive acceleration, and then we come back and then we start moving again and from the other direction. Interesting. That's an interesting graph. All right. So take that as you will. We'll move on to example 4. All right. So for this question, we've got a projectile being launched at a launch angle theta, a given. And at the same time, I've got a cart launched from the origin, and I want to figure out. Need to get some water. How long it takes to find the initial launch velocity such that I can get my projectile to land in this cart. The cart being accelerated from rest by the force F equals e to the minus t. Also, we've got the extra tricky little addition to this problem that 2 seconds after the cart launch, the ball is fired. So there's not only different forces being applied to each of these things, but I've also got a time discrepancy. So 2 seconds after the cart launches, we fire the ball. So that means that our very first time equals 0 will be for the ball, or for the cart. So let's make a force motion relationship in my cart code. So FMR cart is equal to, we'll make this a vector function since I've got 2 dimensions here, 0, not 0, so 0 in the y direction, and in the x direction my force is exp of minus t. And this thing will be equal to the mass times the acceleration in the x direction. So x double dot of t and y double dot of t. So my forces, my force motion relationship for the cart looks like that, and my force motion relationship for the ball, or for my projectile, is very similar. So we'll say that the force in my x direction here is 0. In the y direction, it's minus mg, and this is equal to m x double dot of t y double dot of t. And I'm going to change this to xc for cart, and yc for cart, and xb for the ball, and yb for the ball. I've got them. Oh, looks like I dropped my double equals there. All right. Now we've got our differential equations. All right. So equations of motion. I don't think that we're able to solve the vector differential equations, but we can try. Let me try this real quick. See if it works. Might try this out in Mathematica 9. It might work. I think that they were trying to add this functionality. So x force motion cart, and then our equations are these things right here, and then we're trying to solve with respect to t. Yeah, we're not able to solve with the lists. So there should be no lists on either side of the expression. Yeah, so we have to solve these one at a time. So usually the way I do this is I'll say equation of motion cart x is equal to the x direction of this vector. So you guys remember how we pull out the x component of these vectors? Remember, we dot it with that x direction. So what's a unit vector in x here? It's equal to, oops, I want to write that down here. It's equal to 1, 0. So in the x direction, if I say FMR cart dotted with this, that doesn't work. So I'll say FMR cart 1. Now we'll pull out the first one, dotted with that first vector. So dotted with 1, 0. So that pulls out that first term, and that's equal to The second side of my equation, mark heart 2, also dotted with 1, 0. Alright, so to pull out the y equation of motion, we'll copy that code, and then we'll change these to 2's, and now we need to dot it with a vector in the y direction. So we will do that. So 2, oh, I don't need to change that. What am I doing? Oh, no, this is exactly the same. I just need to change the vector. Yeah. 0 and 1. Alright, so then we'll also create the same thing for the ball. So let's just copy this word, FMR ball. So Control C. Alright, so EM ball. We'll do the FMR ball. Control V. Control V. Put this in the X direction. So this, if this is in the X, then this also has to be in the X. X. And then X direction. Alright, so we're looking good there. Yep, we pulled out the first two terms of each, 0 and mxb, so we just need to pull out our last term. So our equation of motion for the y direction. Y, we'll change this to 1, 0. Or 0.1 rather, 0, 1, and 0, 1. Alright, so now let's solve these differential equations. So desolve this expression, EOM card x slash dot x of t, xc of t, comma t. Alright. We've got our it's yeah, I'm gonna go get a beer immediately after this. Let's see here. X of c of t is equal to this. We have initial, this card is starting at rest. Write that down somewhere. Starting at rest with initial velocity of 0. So let's add that in, these initial expressions. The xc dot of 0 is equal to 0, and xc dot of 0, or xc plane, just the position at 0, is equal to 0. Alright, so I've got our equation with respect to time. Let's now solve this thing. Let's do, we need xc of t slash dot this desolve slash slash first slash slash first. Oops, we don't want to go that many out. We just want to go 1. Alright, there we go. So we'll copy this code and come down here and let's do it for y of c. So y of c for the cart. So we change these all to y's. Initial velocity in all these directions. Y of c, what did I screw up? Oh, I forgot to change that. So 0. So our y of c is always 0. Hey, that's correct. That's good. Everything is tracking well. So now here's the tricky part. I'm going to say cart post. I'm going to say cart post is equal to, and now I'm going to make this a vector. So I've already got my results. I'm going to say this is vector 1. I'm going to put a comma here, and then finishing off the vector there. So boom, now I've got a position vector for my cart position. Now I'll repeat this exact same thing for my ball position. Comes down, change this to ball posts, and this needs to be x of b, EOM of the ball, and this is x of b. That's what I did call it up here, right? Yeah, x of b. Again, x of b, x of b, y of b, EOM of the, oops, probably irreparably screwed up this equation now. Let's see here. There we go. Change this to ball. And we have got YB, YB, YB. All right, so we also have an initial velocity here. So these initial conditions of saying these are 0 are not correct. My initial x and y positions for the ball are at the origin because they start here at 0, 0. However, the initial x velocity will be sine of whatever theta is times my initial velocity. So we'll just say v naught, and, oh, I'm sorry, not sine, this should be cosine of theta. And the initial y velocity will be sine of theta times the v naught as well. All right, so these are in separate cells. So let's see what we've got. For my ball position, I've got the usual kinematic equations of motion. And here I've got this. Let's see. Here's a fast tip if you guys ever want to do this. If you type a / expand, that'll expand out our numbers. So instead of simplifying and factoring things out, so here you can see I've got the expected parametric equation for the ball, the minus gt squared standard gravity plus my initial TV naught sine theta. So everything looks good. The equations are in the right form, and we're ready to actually solve this problem 100% out. So this is really key, guys. As engineers, when we get results, we need to sit back and say, hey, are these results actually accurate? Am I getting a physical answer, or am I getting a result that makes no sense? We already know what the equations of motion are for a particle that's just merely launched into the air. We know what they look like. We have the basic kinematic expression. So if I differentially solve like I did here, all the way out, I would hope that my result takes that final answer. I've got a result that I expect. So in fact it does. So let's find solving this. All right. So I want to find v naught so these things actually hit each other. So I've got two positions here. I've got my cart position and I've got my ball position. Now remember, my ball is launched 2 seconds after my cart is launched. So that means that this time right here is actually different than this time here. And how is it different? This time right here, my cart position is t minus 2 seconds less than this position here. So I'm going to say my new cart position, cart post, is equal to cart post /.t goes to t minus 2 seconds, or I'm sorry, t plus 2 seconds, because this cart has been going for 2 seconds longer than my ball has. All right, so we'll evaluate this. So we'll plug that in. Now we need to solve my cart position. Cart posts is equal to equals ball posts for t and for v naught. Cannot be solved with the methods available to solve. Alas, we'll try nsolve, see if that helps us out. Also not possible. All right, so let's see what the issue is here. Well, first off, let's see how long it takes for this thing to catch up. Let's say that cart posts 1, or my x in my x direction, we'll set this equal to my ball posts 1. All right, so we're setting these things equal to each other, and let's solve this for v naught. So solve this for v naught. We get a result there. All right. So and we've got to see if we've got some symbolic errors here. Cart post is equal to ball position, solve for v naught. Well, let's plug in some constants here and see if we can't figure some things out. Maybe we've got an impossible situation. Maybe it never hits or something like that. Let's set a v naught equal to 5. Let's say g is 9.8. Did I make g negative down here? I did. Our mass will go to, this is the issue. It's the mass of the ball, or mass of the cart, mass of the ball. MB and MC. So we'll make MB B1 and MC B3. Alright, so evaluate this whole section. Alright, so again, checking the ball position. We still got some issue in here. Notice how my ball position depends upon the mass. So I've got a mistake in here somewhere. So let's see if we can track that down. Fortunately, you guys will be getting the good version of this code, so you won't have to go trouble hunting or treasure hunting to find errors. All right, so we're in Y. We've got you solve v sine theta g mt squared. It must be in my here we go, MB. I need to change this to MB as well. All right, problem isolated. So now we'll do the cart position, ball position, and then this. So now come back to the ball position. Hey, we've got our good kinematic expression again. So remember, the basic kinematics don't depend upon the velocity, or the mass of the projectile, which is the case here. All right, so our system can't be solved with the methods available to solve. So let's see cart posts slash dot our constants slash slash n. All right, so we've got a whole bunch of numbers in there. Let's see what our ball position is. Ball post slash dot constant slash slash n. We also need to define what our theta is. So we'll do a slash dot theta. Let's say 30 degrees. Right, so 30 degrees. We'll come back and let's check this out again. All right, let's see if we can figure this out now. So still not able to solve our expression. I'm not certain what the issue is here. Let's say cart position 1, ball position 1, and then let's set a second expression of the cart post 2 equals ball position 2. Still not available. All right, so in these situations, I usually plot my my system to see if there's some parametric plot. I want to plot my cart posts slash dot the constants slash dot t comma 0 comma, let's say 5 seconds. All right, so there's my cart. Let's see, I think we can do line style. I think this will make the line thicker, maybe. Line thick. Plot style, perhaps. It's thick. Yeah. All right. So doing a plot style thick makes our line longer, and I'm also going to start this plot at the origin so I don't confuse myself. So axes origin will set at 0, 0. All right. So first off, it looks like my cart starts out here. So is that actually correct? That's because we set our cart as 2 seconds behind. So we added 2 seconds to it because it had a head start. So from the ball's perspective, the card is really stopping out here. All right, now that we've done that, let's check out the ball position, see what that looks like. All right, well, immediately we see that we've got a rather fast falling ball. So let's say plug this in just to say 2 seconds. All right, and if we plot both of these things at once, ball position, cart posts, cart posts. All right, we need to make our ball either move a lot slower or our cart move a lot slower. So let's set our V naught. Remember, V naught's the thing that we're changing here. So where did I define my constants? Right here. I'm going to take this section of code out. I'm going to come down here. Let's reevaluate these. Put this right in right here. Take this out. Now we're in the same code, and we'll set V naught to be much slower. All right. So see what that looks like. So again, still off. Let's say 3 seconds or 3. All right, let's plot this only out for a second. All right, so you guys see the issue here. A lot of times these equations, when you have actual numerical results or actual constants in, they don't have a solution. So you can see where this card is. I might have to define both theta and t so that I can actually make this thing hit this cart, because this cart is moving quite slowly. So let's change my theta to be a larger number here. Theta to 60 degrees. All right. And then let's increase this even more. Let's say 80 degrees. All right. Not so much. Maybe back down to 70. All right. So these things need to have the same x position. All right. So how am I going to solve this? We've got our card position. I've got 2 position functions with respect to time, and I need to evaluate them, figure out when I can force them to be at the same location. Perhaps instead of solving with respect to t, I'll solve with respect to theta. That's my secret. For those of you, I think some of you know this, I drove all the way back from Dallas last night at like 2 in the morning, so pretty tired. That's my issue here. All right, so that got a hideous result here. I'm going to replace this with my constants to plot this out. Control X. I'm going to re-put this back up here at the beginning of the problem. We'll make this just a reasonable 30 degrees again. And we'll take out this V naught because I don't need that. All right. So found this, and we'll replace this thing with our constants. And holy smokes, that's pretty nasty looking. So we'll also replace this T here. Yikes, that is ugly. Let's do a //n to make sure we've got numerical results. All right, and let's also send our T /.t goes to say 5. All right, so we need to pull out. What did I replace here? Solve for theta is. Is theta accidentally defined as something? Oh, theta is. Let's take that out. All right. Then we'll solve, and then we will Evaluate. All right, great. So now we're good. We're solved for our initial launch angle and my initial velocity. All right, so key point here, guys. When I devised this problem, I made all these problems off the top of my head. I thought that merely just changing the launch velocity would give me enough ability, enough freedom that I could actually hit this moving cart. But you'll notice that I wasn't able to find a solution without both being able to vary the initial velocity and theta. So it took me a while to figure that out, but now I see that I've got to both fire both or be able to change both my initial velocity and theta to get a numerical result. All right here. So first off, I do want to check something very quickly. Let's say pi. I want to figure out what pi divided by 2 is /n. Remember, pi over 2 is 90 degrees. So this theta right here, the one that's a positive result, is this thing says it's nearly firing at 90 degrees. So what does that imply to me? That implies to me that this cart down here, this guy is moving super slowly. Maybe instead of saying e to the minus t, I should have said like e equals t squared or something, so this little cart would be moving. Because with that little small force, the guy's just doesn't seem to be going very, very quickly at all. All right, so now we've got our result. We want to take the positive values here. So that's this one right here. So if we do, we'll put in this notation here, the double brackets and the 2. That pulls out the positive result. And now we'll take that value. I'm going to take out this t over 5. It's no longer needed because it was just used to identify the correct value. We'll suppress this individual output because I don't want to see all that nasty equation, and we'll call this relationship. All right, so we've got that. I'm going to replace my cart and ball position with my relationship, and then my constants, and then let's plot and see if we can get an answer. All right, now let's go ahead and plot these individually within the actual cell. Control V, Control V. Infinite expression 1 over 0 encountered. Oh, don't tell me that. That's no fun. Slash dot t goes to, say, 2. Get a result there. All right, let's plot this thing one position at a time. How long is this our ball in the air? Why is this not plotting a longer deal? 2 seconds, perhaps. Position at 3. All right, what is my ball position? Oh, all right. So you notice that. Oh, here's. Let's do a plot range all. Plot range all. All right. So we've got our ball position. Let's move this out to 10 seconds. 100 seconds. Huh. What about my cart position? All right, well, there's some error in here. I will find it and I will email the code out, and you will be able to figure it out from there. I've been working a long time and don't want to mess with this. This is the issue with trying to solve stuff live. Occasionally you run into errors and you got to figure them out. So, but the basic idea is that we'll set these positions equal to each other, and then we'll go from there. So see if you guys can find where I went wrong later tonight when I send out the